Welcome to Pomodoro Joe for Saturday, May 6th, 2023. Today we're looking at LeetCode problem 1498, number of subsequences that satisfy the given sum condition. This is a medium problem. So you are given an array of integers, nums, and an integer, target. Return the number of non-empty subsequences of nums such that the sum of the minimum and maximum element in the subsequence is less than or equal to the target. Since the answer may be too large, return it modulo 10 to the 9th plus 7. Wow, this is like a medium plus plus. This is like borderline hard problem. So we have an example here. 3, 5, 6, 7, and the target is 9. So in the entire sequence, 3 and 7 are the min and the max respectively. But 3 plus 7 is greater than 9, so those don't work. We'll have to eliminate 7, so we drop out 7, so we get a new subsequence, which is just 3, 5, 6. 3 and 6 are the min and max, and that gives us 9, so that's okay. So 3, 5, 6 works, so that's number 1. Then we can just do 3 and 6. We remove the 5 to get a new subsequence, so it's just 3 and 6. That also works, so that's 2. Then we can drop 6 and just do 3 and 5. Now 3 and 5 become the new min and max, and that's 8, which is less than 9. So 3 plus 5 works, so that's 3. And then we can drop 5 and just have 3 by itself. 3 plus 3 is 6. That gives us 4 total subsequences. Let's see if that's right. We get 3. Yep. 3 and 5, 3, 5, 6, and 3 and 6. So the answer is 4. Oh, right. Okay, before we get started, a quick note on subsequences. What is a subsequence? A subsequence is just the sequence that we're given with 0 or more elements removed. That means given this particular sequence, we can remove, say, the number 5, and then we end up with 3, 6, 7. So 3, 6, 7 is a subsequence of 3, 5, 6, 7. We can also remove 5 and 6, or 5 and 7. If we remove 5 and 7, then we just get 3, 6. That is also a subsequence of 3, 6, 7. Now, I'll note here that the order does maintain. It doesn't change the ordering. We'll still have 3 first, then 6, but in our particular case, ordering won't actually matter, and I'll show you why in just a minute. So now we know what a subsequence is, we understand the problem. Let's put 25 minutes on the Pomodoro timer, and we will get started. Now, as with my usual, I'll put result to start with, and we'll set it to 0. Then at the end, we will return our result. Now in this case, we also have to do result mod 10 to the 9th plus 7. So we will do mod pow. So this is just to be 10 to the 9th plus 7. All right, so now we have our result all set up, and we can start talking about the problem itself. I'm going to do this one a little bit differently today. I'm not going to walk through it the way I normally do. I'm going to point out some of the key concepts, and then we'll work through the problem from there. So one key concept here is just the min and max of our sequence. So let's just grab a sequence here. All right, so in this case, we have this sequence, 3, 5, 6, 7. Now our min will be 3, and our max will be 7. Now this just happens to be the lowest value and the highest value at opposite ends of our list, but they don't have to be in this order. This 7 could be here, and we could have a 4 and a 2. Well, I guess we couldn't have a 2, because that would be less than our 3. So I'm trying to keep things within our range. But we could have other things out here. 4, we could have another 5. Doesn't really matter. So in this case, we have our min and our max. They could be anywhere in the list. We could have things that come before this 3, for instance. We could have a 6, and then 3, 5, 6, 7. And our min would still be 3 and 7. So the min and max and their placement in our subsequence, the placement doesn't really matter. We could have things that come before, we could have things that come after. So in the broad scheme of this problem, ordering doesn't really matter. What only matters here is that we have a min and a max. All right, so now that we've sort of explored our ordering and see that it doesn't really matter in this particular case, there are a couple things that allows us to do. For instance, we can sort all of our values, and we'll get into that in a minute. Okay, first we have to understand that the ordering in this particular problem doesn't matter. our min and max are all that matters, and where they are in the list doesn't really matter. All right, so the next key concept is how many subsequences do we have once we've chosen the min and max? So basically, we can just look at all of the other numbers that aren't the min and max values. So these other numbers are going to be somewhere between our min value and our max value, and they don't really contribute to this target. So we can remove them or we can keep them. It doesn't really matter. So if we keep both 5 and 6, that gives us one subsequence. If we remove the 5, it doesn't really change our min-max value, but that gives us another subsequence. But we could also keep the 5, and we can remove the 6, and that gives us another subsequence. Or we could even remove both 5 and 6, and that gives us another subsequence, all while maintaining our 3 and 7 as the min and max. So let's just rearrange this a little bit, and it might make it a little clearer. So I'm just going to move our 7 inside here. So now our 3 and 7 are going to be maintained. Now I can remove the 5 or the 6 or both. Now what are my options here? Let's just say we have some mapping that tells us whether or not a 5 or a 6 have been removed. So I'm going to have some, let's say it's another array here. 0 means it is there, it hasn't been removed, and 1 means it's been removed. Okay, so in this case, we haven't removed either the 5, 6, so we have 3, 7, 5, 6. All right, that's one valid subsequence. But another one, we could remove the 6, and we have 3, 7, 5. All right, or we could keep the 6, and then remove the 5, and we have 3, 7, 6. Or we could remove both the 5 and 6. So that's 3, 7, 5, or actually just 3, 7. Now we've removed both 5 and 6. Now if you notice what was happening here with these 1s, that went through the entire range of the binary digits. So that basically went from 0, 0 to 0, 1 to 1, 0 and finally to 1, 1. So this is just essentially all the options for all the permutations, I should say, of our 5 and 6. We include both, we exclude both, we remove one, or remove the other. These are the options. So this, if you notice, we have 2 bits. We have a 0-bit, or a 6-bit, I guess, and a 5-bit. So we have 2 bits. Well, how many options did we end up with? 1, 2, 3, 4. Well, that's just 2 to the second power. That's 2 squared. So that's, how many bits do we have? 2. So if we had 3, let's say we can remove the 7, which we actually can, because this 7, even though it's the max right now, we can make 3 the max. So this would be 0, 1, 1, but we could also have 1, 0, 0, and then we can have 1, 0, 1, and we can have 1, 1, 0, and we can have 1, 1, 1. Again, this is just 2 to the third power. So if we have 3 leftover numbers, then we have 2 to the third power. If we have 4 leftover numbers, we'd have 2 to the fourth power. I am not explaining this well at all. I'll probably have to make this video again. So we have our 2 key insights. 1, ordering doesn't really matter because we're just looking at the min and max values. Everything else could be shifted around and the ordering won't make a difference. The second insight is, however many leftover numbers we have that are not in our min and max value, well, then we have that many permutations of subsequences to add to our result. And that will just be 2 to the power of n, where n is the number of leftover digits. Okay, so how do we put this all together? Well, the first thing we want to do is sort our numbers. I know it seems counterintuitive because ordering actually technically matters when you have a subsequence, but in our case, we've already determined that the ordering doesn't really matter. So if we sort our numbers, then we know that our min values will always be on the left and our max values will always be on the right. That's going to be our key here. So our sorted nums will just be sorted nums. So this will sort from min to max. So our min value will be on the left and our max value will be on the right. Now, if we have this min and max value, let's do another little example here. So we have 3, and then we have something up to whatever, in this case 7. That means anything between 3 and 7 here has to be between 3 and 7. So that's kind of good to know. So if we have something like this, and we say 7 plus 3, our min value, if that's greater than our target, then we know that 7 will never be able to match with anything else in our list that will be below or equal to our target, because we're already matching it with the minimum value. So we can just eliminate our 7, just move on to the next one. We go to 6. Then we can say, okay, 3 and 6, well, that's 9. That's great. So now we have our min and our max value, and then everything in between, these are our permutation values. These values we can optionally remove and create new permutations of our subsequences. Okay, so let's keep track of our left and our right. So our low and our high, how about that? Low is going to be at index 0, and then our high will be at the length of our nums minus 1. Okay, so we'll keep track of our lowest value, our min value, and our highest value, our max value. All right, so here's the plan. We'll match our minimum and our maximum values together. If they are less than our target, then we can calculate all the permutations of the numbers in between our min and max values. If it's greater than our target, then we'll have to shift our high index down. We'll have to shift it to the left so we can eliminate that highest value, because it can no longer be used in any of our target calculations. So we're going to be moving our low and our high closer together. So while our low index is less than or equal to our high index. So how do we do this? Well, if our low plus our high, so we'll check our sum here. So if sorted nums, we have to grab our sorted nums here. Actually, let's do this. We can clean this up later. Our min value will be our sorted nums low. Our max val will be our sorted nums at the high index. Now we have to add these together. So min val plus max val. So if our minimum value plus our maximum value is, let's see, less than or equal to our target, then this subsequence is valid, and we can find all the permutations of this subsequence and add them to our result. And as we discussed before, the permutations of that subsequence are just 2 to the power n, where n is just the number of digits in between our min and our max. And in fact, we can include the max itself. So I guess I didn't explain that before. We can actually include the maximum value, because we can drop the maximum value, because the minimum value has to be less than the max value, less than or equal to the max value. So the min value plus itself is a valid subsequence in this case too. All right, so then our result here will increase our result by the number of permutations of this subsequence. And that's just going to be, let's see, well, that's going to be 2 to the power of this n, and n in our case will be our high index minus our low index. That's how many values lie between our min and our max. All right, now that we know that we have this subsequence that works, we can advance our pointer low plus equals 1. So we've exhausted all of the subsequences that use this low value. We need to advance it to the next low value. Otherwise, okay, if we don't have a valid subsequence with this min-max pairing, we know our maximum value must be too large. So we need to decrease our pointer so that we point to the next highest value. So high minus equals 1. All right, so this should be it, I hope. Let's go over this really quick. We start our result at 0. We're going to sort our nums. Now that's going to give us all our minimum values on the left, all our maximum values on the right. So we're going to keep track of our minimum value in our low index and our maximum value with our high index. So we're going to be moving our low and high indices or pointers closer and closer together, while the low is less than or equal to the high index. we'll grab the low value and the high value. If this makes a valid subsequence, then we can add all the permutations of this subsequence to our result. And those permutations are just 2 to the power of however many numbers lie between our min and our max. But we can actually include our max value here. So it's just high minus low. Then we have to move our low pointer towards our high pointer. We need to keep advancing toward moving low and high closer together. Now our high pointer, we only decrement if we know that we can't use this high value anymore. So this high value plus our low value is outside of our target range. We can't use this high value. We move our pointer down. Okay, let's see how this goes. And that works. Let's see if we can pass. And we pass. We do okay. We beat 52% for runtime and 5 or 6% for memory. Yeah, it's not too bad. All right. This one's actually super tricky. I don't know why this is a medium. Honestly, I think this is probably closer to a hard problem. I guess it's just minimal amount of code. Tell you what, check this one out. It's a good one. This is LeetCode problem 1498. It's a tough medium problem. Check it out. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.